Hey, and welcome back to another LeetCode video. This is LeetCode 2598, smallest missing non-negative integer after operations. Right, and it's labeled as a medium problem. This recently occurs as a daily problem. And I wanted to show you a very simple and elegant way of how to solve this. So you're given a zero index integer array nums and an integer value, called value. In one operation, you can add or subtract value from any element of nums. For example, if nums is 1 to 3 and value equals 2, you can choose to subtract value from num 0 to make it minus 1, 2, and 3. The minimum excluded of an array is the smallest missing non-negative integer in it. For example, the max of minus 1, 2, and 3 is 0, because 0 is the smallest positive integer that's missing from the array, while max of 103 is 2. Return the maximum max of nums after applying the mentioned operations any number of times. Interesting. Okay. So let's take these examples here and examine them on the drawing board. Right. So this is what we have. Well, so we have value 5, which means we can add 5 any number of times that we want to our numbers here, right? And I suppose if we have a 1 here, can I resize this? Right, if we have a 1 here, that's already a positive number, so maybe we should keep the 1, right? 10, well, we could add 5 2 times and then it becomes 0. We could take the 7, subtract 5, becomes a 2. We could take the 13, subtract 5 twice, then it becomes a 3. We could take the 6, subtract 5 from it if we wanted, then it becomes a 1. We already have a 1, however, so maybe we want to keep it a 6. And then we have 8. If we subtract 5, it becomes a 3. Or we leave it, well, it becomes another 3, right? So we'd have, well, it could be 2 1s or 2 3s, or it could be an 8. So here in this case, well, 4 would be the positive number that is missing from this array. We have 1, 2, 3, 4. Those are our options, right? So that's what this output is going to be here. Now the same with the array below. Well, so we have a 1 and we operate with a 7 now. So minus 10 plus 14 would be 4, because negative numbers are useless, so we want to turn them into positive ones. If we have 7 and 7, we could subtract 7 to get our 0. 13 minus 7, that's going to be how much? Well, 6. Also, if we subtract 14, it becomes a negative number, which is senseless. And if we subtract 7, it becomes negative as well, so we probably want to keep it a 6. With 8, we can subtract 7 to get a 1. And then we have 1 and 2 is the minimum positive number that is missing from that array. So, so how do we want to transcribe this into an algorithm? Well, we certainly don't want to loop a certain number of times over a value that might be minus 1,000 in order to increase it to a positive number, right? So I think that's going to be a challenge and that we want to circumvent. So what is the quickest way to, let's say, turn minus 1,100 into a positive number? Well, turns out there's a way. So we can use the modulo operator. So if we take mod 5, what do we get then? Well, it's going to be obviously minus 1, but mod 5 will always return a positive number. So that would be 5 minus 1, which would be 4. So we could immediately turn any of these numbers that we get in the array into a positive value between 0 and whatever our value is with the modulo operator. Now, if we had an array where we say, where we keep track of how many times we have a certain number, we know automatically that, this 8, that is 3 plus 5. So, and we know that the 1 plus 5 is 6. So we know that we can turn this 1 into a 6 if we wanted to. And let's say we had an array where maybe we have 3, oops, wrong pencil, where we have, let's say we have 3 values where we can have 1, right? So this might be, wait, this is another one, right? So this is already 3. Delete that. So we know that we have 3 ways, to build. We could build a 1, we could build a 6, we could also build an 11 if we wanted to, right? So having 3 ones means we can build all of these different numbers. We could build like a 16 and all of that. Now, say we have, let's say 3 ways to build a 0, right? Means we can also build a 5, we can also build a 10. Let's say we also have 3 ways to build a 2. So we could build the 2, we could build the 7, right? 2 plus 5 is 7. We could also build a 12. And all of these other numbers that are multiples of 5 plus 2. Now, all we basically need to do now is we need to figure out, well, what are all the numbers that we can build in sequence? Well, we know we can build 3 zeros, so we could say, okay, let's build a 0. Remove one of those. Okay, we can build a 1. Let's decrement our counter. So now we only have 2 ways, 2 numbers left that we can use to build a 1, a 6, and 11. 3. Well, 2. We can build a 2. Subtract our counter. We can build a 3. We have to subtract the counter for 3. Now it comes to 4. Do we have a 4 here? Well, no, we have no 4s to build, right? But if we had a 4, let's say we have 3 ways to build a 4. Well, in that case, we would build a 4, decrement the counter. And well, now we need to build the 5. But 5 modulo 5 is 0, so we're back here at 0. So we could actually build the 5. We have to decrement our counter for those. Then we could build a 6, decrement that counter. Now we can build a 7. We decrement counter here. 7, decrement that counter. 8, we decrement that counter. And 9, well, that's 4 plus, that would be 4, 9. Well, we build the 9, we decrement that counter. Okay, now we can build a 10. Well, we decrement that counter. And now we've run out of ways to build multiples of 5, right? Now we build the 2, the 11. That's this one. We decrement that counter. Now we take the last counter from the ways to build 5 times whatever the value is plus 2, so that will be the 12. And now we want to build a 13, but however, that counter is already 0. So that means, well, 13 is going to be our result in that case. So that is how that algorithm works. We will just iterate through over numbers array, and we'll compute the number mod 5, which will give us back a number between 0 and 5. And then we just iterate from 0 all the way up to however far we get until the counter variable for these values between 0 and our value variable reaches 0. And that's the result. So that's how we're going to do this. So what we need is I guess counter map or a map for the counter, right? Counters. Just going to use a default dict. Now we just iterate over the nums for n in nums. Well, the key is going to be n modulo value. And then we just say counters key plus equals 1. Now we have to figure out, well, what is our max, right? Maybe we should call it max. And the smallest positive value is, of course, 0. So max is never going to be smaller than 0. So that's what we start with. And well, now how do we do this? Well, we say while counters at our index, and that is max value. If that is larger than 0, that means we can build the current value that is max, and we have to increase it. And we have to decrease the counter at the same time. So counter at max percent value minus 1, max plus equals. So let's just run the test cases, and then let's have a look at the runtime complexity. Did I do counter, not defined counters? Right. So in terms of time complexity, well, we have to iterate over the whole array. So that's going to be O of n time. And in worst case, how many memory cells do we need to store all the different values in the different values inside nums modulo value? Well, that is of course m, right? So n is the length of nums, and m is nothing but the value that the variable value has. So that's going to be our base complexity. And now here, you know, how much time do we need to iterate with max? Well, we have incremented the values and counters at most n times. So this while loop is also going to be O of n time. It's not going to use any extra additional memory. So this is O of n time, O of m space. And if I submit this, you see that we get a passing solution. This is slightly more, how could I say this? There's another way of how you can compute this if you wanted to, where you could optimize the second loop here. But it's not going to change the overall runtime complexity, but I just wanted to show you that. So you start with the max value to be affinity. And instead of really having to count up to max, you can simplify this a little bit. So you can just iterate over all of the keys in range value, right? Those are all the residuals, or not residuals, remainders of the integer divisions, all of those modulo values, right? And then all you need to do is you need to say max is equal, well, the minimum between the current max and, okay, now comes a little bit of math. Counters at key times value plus key. Right. So what this does is essentially what we've already seen on the drawing board. We say, you know, how many times can we build back? It's basically how many times can we build the value. Well, we can build the value 3, 8, 13, etc., etc. So what we're going to do now is we're simply doing this index I, right? That is the key times, well, our value plus, of course, the index, right? This would be 0, 1, 1, 2, 3 plus the index I. So basically computing the exact numerical value that can be built with that. So if we have correct. Yeah, we take the count, multiply it with the value. Sorry, so this should not be key, this should be count. This should be cancel. This should be the count, right? The one, oops, that is up here. That count plus value times I. And then, you know, you can calculate that for each, and that gives you a maximum possible max value. But then since this is the maximum, you have to actually take the minimum. And that is where the count is the smallest, right? If all counts are 3 and one have the count of 2, that's going to be the minimum value because I ranges between 0 and value. So the factor of count is the factor that dominates this equation. And that is why that little math thing also works. And now you've optimized this a little bit, so you're not iterating with a loop over n different max values, you're just iterating over m different max values. Let's just run this. And it's fine if you don't see this right away. It doesn't make a lot of a difference. But I just want to show you that this all works.